Welcome to this explainer. Today, we're doing something super cool. We are literally deconstructing the modern AI robot. Looking way past the shiny metal chassis and digging right into the nuts and bolts. We're talking the sophisticated, interconnected systems, the artificial intelligence, the edge computing, the millimeter-perfect hardware. We're going to build a full anatomical blueprint of how these incredible machines actually operate.
I mean, have you ever really stopped to wonder how a robot actually sees and thinks? Just think about the sheer computational miracle it takes for a machine just to walk across a room. For us, our human brains effortlessly process depth, light, dodging a coffee table. But a machine made of silicon and steel, has to replicate that exact split-second decision-making using complex code and raw sensor data. It's wild. Let's break down exactly how it pulls this off. So, here's our blueprint for today. We're going to cover seeing the world, the digital brain, moving and navigating, the connective tissue, and finally, the future of robotics. Okay, before we get too deep, there's a fundamental ground rule for literally every modern robotic system. It's a core loop: see, think, act. First, the robot has to see, gathering environmental data with its sensors. Then it has to think, using AI to process all that data and make a choice. And lastly, act, firing off commands to its motors to physically move in the real world. Seriously, keep this loop in the back of your mind because it's basically the heartbeat of everything we're about to dive into.
All right, starting off with part one, seeing the world, and how robots perceive their environment.
So a robot's vision isn't just a pair of eyes, it's a massive multi-sensor array. On the hardware side, we're talking RGB and depth cameras running alongside LiDAR and radar. But honestly, the real magic is the software parsing all that data in literal milliseconds. Using heavy-hitting frameworks like OpenCV, YOLO, TensorFlow, and PyTorch, the system crunches these feeds incredibly fast. Fast enough to instantly spot a pedestrian, grab an object, or dodge an obstacle dead in its tracks.
And we have to talk about LiDAR. It stands for light detection and ranging, and it's totally the unsung hero here. Picture this. It shoots out rapid pulses of laser light and measures the bounce back millions of times a second. It basically paints a super accurate 3D topographical map of the world. This gives the robot a profound millimeter-accurate understanding of physical space and depth that, frankly, a standard 2D camera just can't pull off. Moving right along to part two, the digital brain, AI and intelligence. Now, this is where all that visual data gets actively analyzed and decisions actually happen. The robot's brain leans on advanced models like machine learning and deep learning, which are powered by some seriously complex neural networks. And thanks to reinforcement learning, robots can actually learn from experience now. Like they'll try a task, fail at it, adjust, and eventually nail it. Plus, with large language models in the mix, these machines can actually understand natural human language. You can literally just speak to it and the AI translates your words right into actionable code. We are way past pre-programmed reflexes. This is active, dynamic decision-making.
Okay, let's look at part three, moving and navigating, the muscles and motion of the machine.
Because let's face it, you can't navigate if you don't know exactly where you are, right? Enter SLAM, that's simultaneous localization and mapping. Imagine waking up in a completely dark, unfamiliar house. As you walk around, kind of feeling the walls, you're building a mental map of the house while simultaneously figuring out exactly where you are inside that map. Well, that's exactly what SLAM algorithms do for robots. It's this absolutely crucial internal map maker that ensures the robot knows its exact location so it can maneuver safely. And I want you to notice the really distinct division of labor here. On one side, you've got macro-level navigation, the SLAM, the GPS, the IMUs, the path planning, basically the stuff asking, hey, how do I get from the warehouse to the loading dock? But on the other side, you have micro-level motion control executing that journey. This relies on hardware like servo and brushless DC motors, encoders, and PID controllers to turn the physical joints with extreme precision. So the brain plans the route, and the muscles execute the steps.
Next up, part four, the connective tissue. We're talking communication and the software stack.
If you look closely, you'll see how every physical function is perfectly paired with an underlying digital technology. Vision needs cameras and LiDAR. Intelligence needs AI. Navigation relies on SLAM and GPS. But to make this whole ecosystem actually work together, the robot has to act as a massive data exchange. This all relies on the bottom layer. Cloud computing infrastructures like Azure IoT or AWS IoT. They act as this overarching nervous system where the physical hardware talks to the wider digital universe. Let's look under the hood real quick. At the core, most modern robots run on ROS2, built over Ubuntu Linux using languages like Python and C++. They use containerization tech like Docker and Kubernetes just to manage software updates seamlessly. For communication, they're leveraging IoT protocols like MQTT over high-speed Wi-Fi or 5G. And all of that connects right back to those massive cloud systems, offloading the heavy processing to edge computing so the robot can think even faster. It is a massive, collaborative stack of tech working in perfect millisecond harmony, sometimes just so a robotic arm can successfully pick up a cardboard box. And finally, part 5, the future of robotics. Let's bring this whole blueprint together. When we pull all these layers together, the complete picture really emerges. You've got AI and computer vision providing intelligence and sight. Advanced sensors are giving it environmental awareness. Cloud computing is handling massive data processing, and automation is enabling true independent action. When you take the seamless, interconnected sum of all these incredible parts working together as one single entity, well, that is the true future of robotics. Which leaves us with one final, pretty massive question. We've seen the hardware, the software, and the AI that brings all of this to life. These machines aren't just tools anymore. They are perceptive, learning agents. So how will our society adapt when these machines can see, learn, and act just as well as we can? It's going to be a profound shift in how we interact with technology. I really hope this blueprint helps you understand the fascinating reality of modern AI robotics. Keep exploring, keep questioning, and thanks so much for joining me for this explainer.